Okay, we're going to take a look at the Doppler effect and run a couple examples just to see how it all comes into play. Here is a picture of the phenomenon right from your textbook, and we have, usually it's a siren of some kind. Here's a police siren emitting a sound source, and if you're seeing this source approach you, the effect is that these wave fronts get compacted. They get compressed together because the siren is emitting sound and then the police car is bumping into it, basically running up to it, so it will effectively make a higher frequency sound. You hear a higher pitch. Now if you're watching this thing recede, you can imagine that these wavelengths are now stretched out. These little peaks and troughs between the wavelengths are stretched out because the cop car is running away from the own sound that it's emitting, and that corresponds to low frequency. Now this is a moving sound source, but it doesn't have to be that way. We can imagine a scenario where you have the cop car stationary but still running its sirens. So you can imagine concentric, really in 3D space, you'd have spherical sound waves coming out from on all sides of the frequency of the source, and you might hear something different because you're moving. Maybe the listener is running towards oh boy, something's wrong with that leg. How does a leg bend? Something like that. I don't know. There's my little stick man running. Haha! And what he's doing is effectively bumping into more sound waves, even though they're stationary. He's running into them, so his frequency would be greater than the source is actually emitting. Now if you're a bad guy, there's no bad guys. They're just people who make bad choices. And this guy robbed a bank, so here's his bag of money, and he's wearing a little mat. Oh, his head disappeared. His little whatever. So here, if you're running away, then you're having the same effect as this observer here, because these sound waves are having to run up to catch up to you. So the frequency of this listener is going to be less than the frequency of the source, and that's just what we call the Doppler effect. It works for all waves, even light, which is pretty remarkable. And we had a general formula for this, that the frequency that the listener hears is equal to the frequency of the source times some factor, and we had to play a little game to make this formula up, but it's 1 plus or minus the velocity of the listener over the velocity of sound, all of that over 1 plus or minus the velocity of the source over the velocity of sound. And there had to be a rule over, when do you choose plus, when do you choose minus, and the rule I suggested is always draw the listener on the left and the source on the right, and that way anything moving to the right gets a plus sign, anything moving to the left gets a negative sign, and then your formula will work every time. So let's see how that pans itself out. Here we have a commuter train blowing its horn and approaching an observer waiting at the crossing. So okay, so here's our observer, and then here is our commuter train, so one of these little kind of things, and it's emitting sound, so it has a certain frequency of a horn. Its source, the frequency of the source is 200 hertz. You are hearing 216 hertz, which makes sense, a higher frequency, because you are being approached by this sound source. We have some other information too. We have that the frequency of the listener. We have that the velocity of sound at this location and temperature is 333 meters per second, and they're asking us, okay, the train's moving, but how fast is it moving? What is the velocity of the source? Well, let's take a look. If we look at our original equation here, what you'll find is that if the velocity of the listener is 0, if he's stationary, this whole term equals 0. So 1 plus or minus 0 equals just 1. So that's going to reduce our formula, make it into something a little bit simpler, like the frequency of the listener equals the frequency of the sound times 1 over 1 something, velocity of the sound over velocity of, the velocity of the source over the velocity of the sound. Is it a plus or a minus? Well, let's see. He's moving to the left, and the way we draw these pictures is that to the left is negative. So I'm going to choose the negative sign here. I'm going to put the negative sign in there, and let's see what happens. So if I drop some numbers in, I get, he hears 216 hertz. The emitted sound is 200. 1 over 1 minus velocity of the source, I don't know. The velocity of sound is 333 meters per second. So that's my equation, and now it's just algebra. But that can still throw some folks, so here's a couple quick steps you could do. You could divide both sides by 200. That makes that turn into 1. This ends up being 1.08, it turns out. And then this equals this weirdo fraction here. And then if you use cross multiplication, you can flip this guy. So we're slowly digging out this velocity of the source. So then you end up with something like 1 minus the velocity of the source over 333 equals 1 over 1.08. And then you can subtract 1 from both sides. So you're seeing kind of the pattern. And eventually what you can do is dig out the velocity of the source, and what you're going to find is that it is 24.7 meters per second. So that is how fast the train is approaching this observer. Okay, so that sounds good. Now what happens when the train goes in the opposite direction? Now again, I'm going to draw this the same way, but the train now is pointed this way. So here's our train zooming away, rather than to have the source on the left-hand side, just to maintain what we've been talking about. And we don't know the frequency of the listener now. We don't know that, but we do know the velocity of the source. We just found it. It is 24.7 meters per second. And we still know that he's got the same horn of 200 hertz. So what does he hear? Well, excuse me. Well, let's see. We're looking for the velocity, the frequency of the listener, and now we have a source that's moving away. So I think we're going to want to choose the positive sign in that equation now. So let's see how that's going to look. That's going to be frequency of the listener equals the frequency of the source times 1 over 1 plus Vs over V. So a similar situation. What does he hear? Well, it's going to be 200 times 1 over 1 plus 24.7, that's his speed, we found that from the other problem, over 333 meters per second. That gives us 186 hertz. That is less than the emitted sound from the source, so that totally makes sense that you would expect this. Now you can have we're not doing a problem like this, but you could totally imagine a situation where this guy is moving too. Maybe he's running away or running towards. All you got to do is pick the plus or the minus to go in the numerator and just put in his data, and the formula takes care of the rest. It will tell you if it's going to be a higher frequency, lower frequency. Even when they're both moving, this formula will work. Okay, so I chose another little one that I thought was kind of interesting. Here you have a tuning fork, and you get it vibrating, and then you drop it off a building. So here is our little tuning fork. What is that little? Looks like a wishbone or something, but it's vibrating, and then you just let it fall off of a building. And as you might imagine, as things fall, they pick up speed, they accelerate. So initially, our source is 623 hertz, but we want to hear 595 hertz. Isn't that interesting? So we have to figure out how far is this thing going to fall before it's producing that sound. So that's interesting because they're asking us about a distance. Well, I like this question because it makes you go back to stuff we've already looked at. The question is, it's asking how far, but our formula depends on how fast. So that means there has to be some sort of target velocity. A velocity of the source is going to be hit. Once it hits that certain value, then we're going to hear this tone that we want to hear. So what we really need to do is find this first, and then once we find that velocity, then we can find how far it's fallen in order to have that velocity. So let's take a look at this. So now we have a moving source again, and according to our arrangement here, the source is moving away from the listener. So I could kind of draw this as the downward direction being positive in this case, and I could have a very similar formula for the Doppler effect. We can see that the frequency of the listener equals the frequency of the source. The listener is not moving again, so the top part just turns into 1. The denominator stays alive, and there's going to be a plus sign because this source is moving in the positive direction. And tells us to use 343 for the velocity of sound. So basically, we want to look for a scenario where I do hear 595 hertz from a 623 hertz source. So that means we're solving for the velocity of the source when the velocity of sound is 343 meters per second. So you drop these numbers in, and what you're going to find is that the velocity of the source is 16.14 meters per second. But that's not the answer to the question. They're asking us, how far has it fallen? What is x? In order to get this velocity. And what I like about it is it reminds you that all these things, even though we study different units, they're all tied together. It's all physics. And so in this case, I would have to consider this to be a kinematics problem, that this thing is constantly accelerating down at a value of 9.8 meters per second squared. And so that means all my kinematic equations still apply. The most valuable one, I think, for us right now is what we call the third equation, that the final velocity squared equals initial velocity squared plus 2 times the acceleration times the difference in displacement, in this case vertical displacement. So let's see, how far do I fall if I have a final velocity of 16.14 meters per second. I'm dropped, so my initial velocity is 0, and I'm accelerating at 9.8. I'm going to use a positive value because we're calling down positive here. And let's see, what does x turn out to be? Well, when you run this, you end up getting an x value of 13.3 meters. So it's amazing what physics can tell you. That's how far the tuning fork has to fall in order to hear this sound. So these are a couple examples. You can try some on your own and then bring them in to me, and I can double check them for you, but I hope that helps.